Alright. So anyway, today's the lecture on the acid-fast stain, and we're going to talk about history, theory, and problems. And the problems can be summed up in one word: the genus Bacillus is our problem. And we'll be talking about that a lot. Then after we have our little lecture on the acid-fast stain, we're going to have a pop quiz on the acid-fast stain. And then we're going to do lab for 2.5 to 3 hours on acid-fast staining. And if you finish with the acid-fast stain, you can go back and pick up anything you missed on the gram stain or the negative stain. Next class, that means Wednesday, we're going to be doing the easiest stain to do, the hardest one to read. And the easiest one to do is the endospore stain. I mean, it's just 2 colors with water in between. Incredibly easy to do, but incredibly difficult to interpret because you've got to actually think. I know, you don't just jump at a color. And the hint on the endospore stain, remember, if it keeps the first stain, it's positive, and if it keeps the second stain, it's negative. Remember that? Forget it all. On the endospore stain, I want you to forget the color green. The color green should not enter your mind. Green, forget. I don't think of green. Okay? And that's, we'll be talking about that in a little bit. The key to the endospore stain is one word: holes. Like in your brain, cheese, holes. Okay? All right, or in your head. So anyway, we'll talk about endospore stain interpretation, theory, problems, and we're going to have a pop quiz on reading all the stains, and it's called Name the Stain Game, and that will be the pop quiz on Wednesday. Monday, we will finish Chapter 3 lecture for the first hour and a half. Then we will go into a simulation phase, you know, like when the nuclear bomb is about to hit and they simulate a nuclear attack. Well, we're going to simulate a lab practical 1. We're going to have 100 multiple choice questions, and you're going to get a number 2, and you're going to pretend you're taking lab practical 1. And it'll count as a little chapter quiz, but it will be to stimulate your studying, and so that you can know by the time you walk out what you're not prepared for the next class, which is Lab Practical 1. And Wednesday of next week is Lab Practical 1. It will be all Lab Practical 1. Good news, when you walk in the door, you will never say another word. There will be no speaking, no sounds, nothing. The only thing you can do when you come in is grunt. So you will come in, you will sit down, you will take 200 multiple choice on an 884E. I hope I wrote that down, but I didn't. So this one is an 884E. Stands on for the lab practical. 200 multiple choice questions over the microscope, focusing the microscope, care of the microscope, everything about smears, everything about stains, theory of stains, hypothetical situations on stains, everything you can ever think of that we've gone over, and maybe 1 or 2 questions on what's the word organized mean? You know, always go back and pick up 1 or 2 on the previous. That'll be the lab practical next Wednesday. Tonight at 9:30, if you took the retake, I'll have that little essay back for you. If you brought me your stick, your clue notice, please put it on my briefcase before we leave tonight so that I can up your grade, your multiple choice on the last test. After we take the lab practical 1, the class after that, bring in what you have done, and you better have done something, on the procedure cards. Now, I don't want them in final finished form unless you're, confident of them. If there's some that you're very confident, like MBIT, all MVIC is a chart. And the purpose is to determine if the gram-negative rod you see under the microscope is E. coli, which is an indicator of pollution, or something that looks like E. coli. And then you put a little chart. And it's called MVIC, which is indole methyl red Vogt Proskauer citrate. And if you're positive on the first two and negative on the second two, you're E. coli, and if you're something else, you're not E. coli. So that would be a very easy card that you would not need to have any brains about, and you could just go ahead and make a final copy of it. Bring in your cards and bring in any questions on how to make any of your procedure cards, because that's the last day we're going to discuss anything about procedure cards. We will assume that you understand how to make them, and you will go home and make them, because I will then give a 30-minute lecture on how to make the 25 blue or experiment cards. And then you will have 1 week to finish the blue or experiment cards, and those are the big ones, the important ones. So the day after Lab Practical 1, you bring in your procedure cards as far as you've gotten them, either on a sheet of paper or whatever, any questions you have about them, the finished ones that you've already got done, and anything you want to go over on procedure cards. I will then lecture on the experiment cards, the last 25, how to do them. Then we will start the lecture on chapter 9, which is taxonomy. So that's the class after Lab Practical 1. Any questions about what's coming up? Yeah.
For the procedure cards, all of them are due?
All of them.
The day after, I mean, on the Wednesday of.
Right. And shouldn't be hard, since there's 2 sets of them online. All you have to do is just go look at them and compare what I wrote down about them and how you would write that and put yours together.
And is that whole list?
Yeah. You go under, everybody knows where to find it, right?
Mm-hmm.
Everybody know where to find the check cards. Check and see if you're right or wrong. Okay, let's look to see where you find the check cards. You can go on to the Dropbox. There's a set of cards there. Or you can check are the thermostats on super cold?
Don't.
Come on. There we go. All right, so if you go to midterm lab practical 2, and if you go over here and it says practical 2. Unknown cards button. And there should be one called check your cards, but somehow it's not here. Down at the bottom of it. Unknown cards. Summary sheet. Somebody send me that, and I'll send me a question, and I'll make sure that appears for some reason. Oh, there's where it is. Okay. I'm going to drop it on this one, right? There it is. Is it this one?
Well, if you on the bottom, you click your unknown that. And then it says check your unknown cards list. And then when I click on that, it says check your cards here.
Here, right?
And on this side, it should go.
Yeah, mine said it too. Maybe it's over here on the side and I just don't see it because it's hanging on. There it is. Check your cards here now. Sorry about that. I knew it was there. And if you go down to the bottom of the page, it has all the cards you should have, although these are not like A set cards, they're B- cards. And the one's for drops, the one for gram stain, and so forth. So, anyway, that's that. And I don't want to belabor that anymore. So let's go back to what we're doing today. That is, we're going to do everything acid-fast stain today. And we're going to be talking about the Zeal-Nielsen acid-fast stain. And we're going to be talking, it is for 2 genera. So who can tell me the 4 things that differential stains tell you? Number 1. Chemistry. Something about the chemistry. And for instance, in acid-fast staining, what does it tell you? Presence of lipid layer. Lipid layer is the chemistry. The chemistry for gram stain was?
The cell wall thickness.
Cell wall thickness. This is lipid layer. Alright, and it divides all bacteria into at least 2 categories, and the 2 categories for the acid-fast stain is acid-fast and non-acid-fast. So it is just 2 categories. Then it tells you that if you put the first stain on and it retains that at the end, it's positive. And if you put the second stain on and it retains that at the end, it's negative. And so that's a third characteristic of differential staining. And then they, of course, all start with a smear. And this particular one, the 2 genera that stain acid-fast are Nocardia and Mycobacterium. And they are gram-positive, but what's unusual about their being gram-positive? They look gram-positive under the microscope when you do the gram stain, but intellectually we call them what? Do we call them gram-positive, or what do we call them? Gram variable on the positive side. So there's gram variable on the positive side. That's because they usually are 80% positive, 20% negative, and the reason that a few of them stain pink is that the crystal violet is dissolved in alcohol and water, and lipids repel water, so a few of them don't take up the crystal violet. A few of the bacteria won't take up the crystal violet. All right. The genus Mycobacteria is the one we're going to concentrate on. Every generation has a bugaboo, a disease that scares the hell out of everybody. Ours was AIDS, our parents was polio, and our grandparents, your great-grandparents, my grandparents, it was tuberculosis or consumption. And so this disease, consumption or tuberculosis, is one of the few in Mycobacterium. In fact, Mycobacterium, all the species in Mycobacterium are deadly except for a very tiny few. They cause horrible things like leprosy. And everybody knows about leprosy, you know, 5,000 years in the Bible. You can read about people having leprosy. And they were considered filthy people. It actually wasn't filth that caused the leprosy. It was living in very close proximity with someone who has it will catch you the disease. The disease is contagious, but only if you live with someone a long period of time that has it. The Mycobacterium bacteria doesn't like 98 degrees Fahrenheit body temperature. It likes cooler areas, and so that's what gets infected and falls off. So fingers fall off, and noses, and lips, and ears, and hee-hees fall off. And yeah, you go scratch your ear, and it comes off in your hand. So the leprosy is a tremendously negative disease. It has very bad reputation. You can still see people in South America on a little wooden cart with roller skate wheels pushing themselves around the sidewalks begging in Brazil, for instance, that are lepers. People that have lost their feet and so forth, and they'll have their hands all bound up because they won't have anything but nubs. We used to have a leper colony in Louisiana and one in Hawaii, where people with leprosy were sent so they wouldn't pass it on to other people. The microbe is incredibly difficult to kill. Why is Mycobacterium so difficult to kill?
Because of a thick cell wall.
Thick cell wall containing
Lipids.
and why are lipids make it difficult to kill? What are all your disinfectants dissolved in? Water. And what happens when you spray a water with a poison dissolved on it and on top of a lipid? Repels it. So most of the hospital disinfectants and things we use don't affect Mycobacterium, leprosy, or tuberculosis because that lipid layer protects them. Now that lipid layer is like walking around with 20 feet of fat on the outside of you. And so if you think about it, a person that would have this much fat around them would have a hard time getting sandwiches in and getting the poop out, right? Think about it. If you had a huge fat layer around you, how would somebody get food to you? It would have to dissolve through that huge lipid layer. So Mycobacterium grows very slowly. For what reason? Again, the lipid layer. How does the lipid layer prevent rapid growth? Prevents the diffusion of food, diffusion and osmosis of food in and waste out. It protects it because so many of the disinfectants and poisons that we use to kill bacteria are dissolved in water, and the lipid layer repels that water. It also protects it from drying. So you will see in hospitals, it will say there are airborne controls for the following organisms. And nobody has to worry about smallpox anymore unless, you know, Russia or Assad or somebody else that still has the weapons. Because remember, the United States and Russia and several other countries weaponized smallpox and put it in shells. And it was against the law, and we didn't do, and you know, we said we'd never do it, but they did it, so we did it. So there are probably still smallpox weaponized shells that could be used to shell or explode in a population, and probably nobody in here has been vaccinated for smallpox. So that is, remember, there are two places in the world where smallpox is kept, and that's Russia in a laboratory and in the CDC in Atlanta. And the little scabs that people get when they get these poxes all over their body, and we're talking about every square centimeter of your body is covered with a weeping pox. These little scabs move through the air more than 6 feet, so it's considered airborne. Tuberculosis, because it's resistant to drying because of the lipid layer, stays on dust and travels for hundreds of feet. So it is also considered a airborne disease. So smallpox and TB, Mycobacterium are both airborne diseases. And anyone know the other one? Chickenpox. Chickenpox is also That's why if you've not had chickenpox or had the vaccine, you can't work on a ward where people have chickenpox because it is airborne. Meaning, what's airborne mean? It means it moves on the dust and through air currents for more than 6 feet. Now somebody goes, that's called droplet transmission. It's not airborne. It's droplet. It's how far a spit droplet can go. And by gravity, that's about 1.5 meters to 2 meters. So 6 feet, 2 meters is as far as droplets can go. So cold and flu is droplet transmission, not airborne. What 3 diseases are airborne? Smallpox, chickenpox, TB. Which one are we talking about? TB. All right, tuberculosis, and what's the old name for it? Consumption. In the 1900s, it was called consumption. It can involve more than the lungs. It can eat up your internal organs. So that's why it was called consumption. And people would look like they would be consumed from the outside. They would become skin and bones and throwing up blood and so forth if they had the lung one. There are about 150 different species of Mycobacterium. And only 3 are considered harmless. And of those 3, one of them looks like human tuberculosis, grows like it, stains like it, appears in every way to be like it, but won't give you the human disease. And it's called Mycobacterium pseudotuberculosis. And it would be perfect for us to use in this laboratory because it is so much like the real human one, but doesn't cause the disease. That's the problem. We can't use it because it is so much like the human one that they would shut down the campus and probably a mile in all directions and force everybody to have skin tests. Because you can't tell pseudotuberculosis from tuberculosis without a DNA test of the bacteria, which takes time of about a week. So the kind of Mycobacterium that we use, the one we use is Mycobacterium smegmatis. And it grows under the foreskins of human males. It is not associated with any disease except it is associated in people that have no immune system with Crohn's disease. People that have very low immune system, very old or under chemotherapy or radiation therapy, when they get these lesions in their intestines and they have Crohn's disease, many times they've isolated Mycobacterium smegmatis from that. No one knows what the relationship between smegmatis and Crohn's disease is, but it has been found in a lot of people that have the disease. We don't know if it took advantage of the situation or if it had some causative reason. Anyway, this is the one we work with. It is a very small rod that is clear, and it has a nucleus toward the fat end, not the sharp end, but the fat end, that is electron dense. And so when it stains on the gram stain, lots of people say, oh my goodness, it's a cocci. But it's not a cocci because you're forgetting to look at the rest of the rod. And just because this is dark purple in the round area doesn't mean that the whole microbe is round. It is a rod, a very small rod with a fat end that has a dark electron dense nucleus in it and a pointy end. It is gooey and sticky. So when you try to make your smears tonight, you're going to have a hard time getting it off the auger. It's going to seem like a scab. And when you get it in the water, is it going to dissolve or be repelled? Be repelled. So you're going to have to take your loop and beat it to get it to fall to pieces. So that otherwise you're going to get one huge black glob. So remember, it is a difficult microbe to work with, but you do need to see it. because it does grow, look, and stain like the rest of the Mycobacterium. All right, then there is a whole bunch of different kinds of Mycobacterium. There's a whole bunch of different bird tuberculosis and a bunch of cow tuberculosis, and we even have reptile tuberculosis. People don't usually get anything but the human one, the bird one, and sometimes the cow one. So that's why in the old days, if you went over to somebody's house and they said, would you like something to drink? They didn't offer you milk. Nobody drank milk in those days unless you knew the cow personally. Because whatever cows get, we get. And they have TB, and so we wouldn't want to give people TB. So we developed things like cottage cheese and yogurt and cheese and so forth for our milk products, and they would outcompete, the bacteria in our yogurt would outcompete any of the pathogens, and that's why whenever the doctor says, oh, let's give you some antibiotics and you poop everywhere because it kills your friendly bacteria, what do they tell you to eat? Go eat a live yogurt culture and repopulate your intestines with the friendly bacteria that will outcompete harmful ones. So anyway, remember that the avian used to be a leading cause of death in people with AIDS. It was called MAC. And it's called Mycobacterium avium intracellulare. MAC. Avium means bird, and this is the reason why you can't go to South America, find a nice parrot, and bring it home. You can't bring birds into this country unless they've been tested for MAC. Mycobacterium avium intracellulare. Why? AIDS patients, people with immune problems, people with cancer, radiation therapy, steroid therapy, and very old people can die of bird tuberculosis. All right, so that's a little bit about Mycobacterium, the genus, and the one species that we can work with. Let's talk a little bit about the history. Whenever you talk about Mycobacterium, one guy's name comes up, Robert Koch. And Robert Koch was a German, and he was a young man in the early 1900s, while Louis Pasteur, the father of microbiology, was an old man. All the wonderful things that Louis Pasteur did for microbiology were old hat in the 1900s. Remember, Louis Pasteur, what did he do? He proved that microbes are the cause of contamination and disease. It's called the germ theory of contamination and disease, and he did it with that swan neck flask. Remember? You read chapter 1, swan neck flask experiment. If you go to the Pasteur Institute, if you go to Paris, France, take the subway, you can get off at the Institut Pasteur. Go upstairs to the museum and see the actual swan neck flask that Louis Pasteur put chicken soup in and disproved Aristotle's spontaneous generation theory. Remember, Aristotle, who didn't have much to work with, since he was the very first scientist, said that life comes from the 5 great elements of the universe added together in the right proportions. And those 5 great elements were air, fire, water, earth, and the breath of God. If you put them in the right order, you would get living things or anything you wanted, which led to the pseudoscience of alchemy, which was a science in the Middle Ages of changing anything into gold or silver or precious stuff. You put the right combination of what elements? Air, fire, water, earth, and the breath of God. And Pasteur said that's bullcrap. He said life comes from other living things. It's just living things are smaller, lots of them are smaller than the human eye can see. And he called them germs. And he said if life comes from, if the 5 great elements combine to form living things, and if I put chicken soup in here and leave it, life will pop up in there. Of course, then he would have people come around, you know, breathe the breath of God on it, or do some hocus pocus or whatever. He put chicken soup in here, he heated it to boiling, and he let it set. 5 weeks, 8 weeks. It's still setting there. 100 years later, it's still setting there. Pure. Not contaminated. And he said, you know, say all you want. Remember the first experiments by Reddy and all of them? They had a container. They put soup in there. They heated it to red hot, and they put a stopper in it. And the scientists said, well, dead things should come into life there, and they didn't. And they said, I've disproved spontaneous generation. And what was the criticism of this experiment?
There's no air.
Not air. Well, air was, some people said air, other people said breath of God. Breath of God could get in there. He bounced right off. And then they put cotton wads in there. That's what Pasteur did first. He did his chicken soup and he put cotton in here. He said, not only can air get through there, but God can too. And they said, nope, God bounced off cotton. So, yeah, I always thought that was very strange that their gods were omnipotent, but they bounced off cotton. You know, God can bounce off a condom too. And you know you can prevent God. Yeah, you can prevent babies by using a condom. If God wants you to have a baby, you can stop him. Omnipotent God. All right, so anyway, why did Pasteur's experiment work? He heated this to boiling. It sterilized the interior. Created a water trap here. Any air containing dust would be slowed by going around this vent, and the dust would fall out. So by the time air got here, it was sterile. And that's still there in Pasteur Institute. So anyway, Pasteur was a very, very, very famous guy. He came up with the second vaccine, the rabies vaccine. He developed originally for animals, and then it was used on humans. And so he was, if you look in the Bible of microbiology, which is Berge's manual, you will find about 20 to 30% of all the bacteria ever described. It will mention Pasteur first described it and saw it. So he's a very big guy, and Koch was a German, and he wanted to be as important as Louis Pasteur. Now, the French and the Germans have always been best friends, right?
No.
Are you kidding me? Franco-Prussian War, the 100 Years' War, World War I, and World War II, between basically the French and the Germans. And even now in the European Union, they're always at each other. So the French and the Germans have never been good friends, and Koch was very jealous of Pasteur's very famous in science. He was the world's greatest scientist. So he decided to work on the greatest disease of his time. And that was Mycobacterium, tuberculosis. Well, the problem was no one had ever proven the cause of tuberculosis. Not only had they not proven any microbe as the cause, but of course no one had been able to grow it, or isolate it, or stain it, or see it, or anything. And so he spent quite a bit of time, and he came up with something you've got to look up and know, and that is Koch's postulate, the biggest discovery in all of microbiology. After the discovery of microbes, Koch's postulates is the discovery in all of microbiology. It is a series of 4 statements that proves, have you ever heard that word in science before, proves? Because you don't hear it very often. Proves that one particular specific bacteria or microbe causes a certain disease. The word prove we never use in science, hardly ever. So when someone comes up with a series of 4 simple statements that can prove that a certain microbe causes a specific illness, any illness that's big. And so Koch's postulates is this. If you want to know what causes an illness, find an individual with the illness. Isolate the microbes from the area of the illness. Separate each one out. Put each one in a test animal. The one animal that shows the same symptoms as the original illness, re-isolate it, compare them. If they're the same, that's what caused it. And so, because of Koch's postulates, every vaccine and treatment and cure we have today, because how can you cure a disease if you don't know what causes it? How can you make a vaccine if you don't know what causes it? You've got to know the microbe that causes it before you can do anything. So everything in infectious disease is due to Koch's postulates. That should make him the father of all of microbiology. It doesn't, and we'll talk about why. So anyway, first he came up with Koch's postulates, and then from sputum, everybody knows what that is? That's sputum. From the sputum of people with tuberculosis, bloody sputum that they cough up, he isolated the gram-positive, now we know gram-variable, microbe that causes it, Mycobacterium tuberculosis. He isolated the bacteria. And it wouldn't grow, it grew so slowly. And he discovered by adding certain nutrients to agar how to grow it in the laboratory. But it's also because it resists stains dissolved in water. It was very hard to stain, so he also developed the stain to stain Mycobacterium. So what 3 things did he discover about Mycobacterium? He discovered it was the causative agent. He discovered how to grow it and how to stain it. And for this, he received the very first Nobel Prize in microbiology. Pasteur never got a Nobel Prize. Why? Because he was old and all his discoveries were old hat by the time the Nobel Prize was established. So the greatest microbiologist to ever get, and the very first one to get a Nobel Prize, was Koch. What else did Koch do? He set up the first microbiology class. He set up the first microbiology university laboratory. He set up the first university lecture and laboratory for microbiology. He discovered the causative agent of anthrax in cows, which people and sheep and horses and other animals can get. He worked on yellow fever and so many other things. But what was Pasteur also famous for? What did he discover besides the germ theory and importance of washing your hands and the sterile technique? What? The rabies vaccine. And so Koch wanted to make a vaccine for Mycobacterium. Now the rabies vaccine was made by taking an infected rabbit and drying the spinal cord, because that's where the microbe was located, in the nervous system. And by drying the spinal cord, you damage the microbe so it couldn't cause full-blown illness. So Koch decided he wanted to damage tuberculosis, so he tried heat treating it. What do you think heat does to lipids? Not much. And here's the problem. If you're going to make a vaccine, you start in the laboratory, and then you start on laboratory animals, and then eventually, after it's successful on animals, you do a few experiments on people that are, terminally ill, and if that's successful, then you do some controlled experiments on a very small population to see if it's toxic and deadly and blah, blah, blah. Nope, he started with people. And he started with volunteers. You know how Germans get volunteers. Okay? Street people, people in jail, people in prison, people who didn't have much choice but to volunteer. And since he heat treated Mycobacterium, he didn't kill it well. So he actually ended up infecting people in his experiments. Now, what do? If you're a newly formed country of Germany, it just newly got all the principalities together, became a united country, what do? If the greatest scientist in your country, who won the world's first Nobel Prize in microbiology, kills people?
Try to cover it.
Try to cover it up. That's an American way. Yeah? All right. So in Europe, you know, when somebody kidnaps some little 5-year-old kid and drags them off into some sort of hostage situation versus the United States. If a kid gets drug off into a hostage situation here, what do? We surround the house, we take a bullhorn out, we say we're going to blow you up, we're going to kill you, and we're going to shoot everyone there. You have 5 minutes. And then we go in and kill everybody. You know what they do in Europe? They surround the house, cut off the electricity, cut off the water, and they sit there and they wait. Getting hungry? Cheeseburgers, croissants, espresso. Oh, you don't have any. No water either. And they just wait them out. What do? We shoot them dead. That's just the way that people do things differently. So, if Koch had done what he did in the United States, we probably would have hung him. Something like that. We didn't have the electric chair much then. But we didn't. He didn't do it here. He did it in Europe. And so Europe banned him from Europe. He was banned from civilization. Sort of like what they did to Napoleon. Remember? They got him. They put him on this little island off of Italy called Elba. And then they made fun of him by giving him like 6 people to guard him and called him the Emperor of Elba with a population of 6. You know, because he had these great ambitions, you know, to rule the world. But Napoleon, remember, escaped. And the next time they caught him, they took him to St. Helena, which is halfway between South Africa and Brazil. Probably the worst island on the face of the earth. It rains 366 days a year. And the national flower is a fungi. And it has cliffs around it. You basically have to helicopter people in. And Napoleon ended up dying there, writing his memoir. What do you guys think about Napoleon? Everybody, how many of you think he was okay, freedom fighter, whatever, for France? How many people think he was as bad as Hitler? He killed almost as many as Hitler if you don't count the Holocaust. He killed hundreds of thousands of people. He used to have 10,000 people take their guns and march toward each other. And then he would say, oh my God, it looks like the Hungarian front's falling. Throw in 5,000 more Prussians. At the end of the day, he was famous for saying, what was the butcher's bill for today? How many tens of thousands of soldiers did I lose? Because he thought he was going to be Emperor of Earth. God told him he was going to be Emperor of Earth. So anyway, this guy was banned from Europe. Now, he wasn't that stupid. You know what he did? He went to Africa and he worked on yellow fever and malaria and tried to make up for all his bad things, and then he discovered he could make a lot of money giving speeches. So he spent the rest of his life making money hand over fist in the United States and Canada giving speeches. So not so bad a punishment, really. Koch is famous for his postulates. He should be the father of microbiology. He did much more than Pasteur, but why isn't he? He killed people. Now, to this day, it still messes with our brains. Can you believe a mistake of way back then still affects us today? Why? Because everywhere else in the world, if you go to the United Nations World Health website and you ask what childhood vaccinations are recommended by the World Health Organization for every child in every country in the world, you will find this one. BCG. It's tuberculosis. It's a vaccine, killed vaccine, that prevents the most common form of tuberculosis. And 178 countries give it. One doesn't. What one do you think? The United States does not give the BCG vaccine. Why don't we give it? One, there's still that thought in our head, can you really kill Mycobacterium? After all, remember what happened? People got the disease. So there's this bias about killing it, and we want the skin test to work. The skin test costs 25 cents. What do? They take live tuberculosis bacilli and they inject it just under your skin. And if your body has ever seen tuberculosis, meaning you've been infected or exposed to it, you will have antibodies that will show inflammation, or a little circle around that, which they then measure. And if you're positive, then they will make you take the medication. Now, the sad thing is, in the United States, they don't realize there are other countries in the world. Do you know that? Here, we do not believe anybody exists but us. Me. So, if you grew up in South America like I did, or any other country, you had BCG. And 60 to 70% of all people who had the BCG vaccine as a child are going to be positive on the skin test, the tuberculin test. Which means the United States law does not provide for that. The United States law says if you're positive on the TB skin test, you must take the very harsh antibiotics for tuberculosis. So every 3 years I have to prove I don't have TB. Every teacher in California has to prove every 3 years you don't have TB. So I get an email. Go to the Student Health Center and get a TB skin test. And I email back, no. I had BCG as a child. I was positive. I will always be positive. That doesn't work on me. And they send me back. State law requires that you go. So I go. I sit down and they say, what are you here for? And I said, the TB skin test. And they said, your records say you're positive. I said, I know, I had BCG. They said, then why are you taking it? I said, because state law says I have to. So they give it to me. And guess what comes out? Positive. And guess what they tell me? You've got to take these antibiotics. I said, no, I'm not. I'm not taking those. I'm not positive. They said, state law requires that you take these antibiotics. So I said, how can I get out of it? And they say, you can pay $175 for a better blood test, but you have to pay for it. Or you can pay $75, but get radiation and go get a chest x-ray. And I have to do this every 3 years, either pay $175 for the blood test or get a chest x-ray. Because they don't make anything to respond to people that are from another country. Now, if you go to Adventist Hospital or County USC and you work for 3 years, you will skin test positive. No doubt about it. If you're a nurse, you will skin test positive. Does this mean you're infected? No. It just means it's a public hospital with a lot of poor people that come in there that have it, and it's in the environment, and you're breathing it in enough to give a positive skin test. You won't be positive, but you'll test positive, and then you'll have to go through the same crap I go through. So, you know, a lot of my students actually go to Tijuana, which they have a very modern health department there, and they walk in and they say, I'm from a poor country that won't give BCG vaccine. Will you give me one? And they will give you one free, so that you will be protected against tuberculosis like everyone else in the world. It's not against all forms, but it's against about 60% of the forms that we get in the world. And Mexico will give it to Americans for free because they feel sorry for us. Just FYI. All right, so that's the history, a little bit about Koch's postulates. Now we're going to talk about the theory and the stain, how it works and why. So, the acid-fast stain, you're going to get a properly made smear, and remember I'm going to show you in a few minutes how to do it, but you're going to get a properly made smear and make sure it's thin. And by the way, remember this one, if you're doing Mycobacterium, and we all want you to do a Mycobacterium, but if you do it, remember those chunks, you've got to beat them. You get them broken up. All right, and then you're going to take that circle, and by the way, this is one where you're going to have your slide like this, and you're going to put your little circle a little bit past halfway, and you're going to make your smear here, and then you're going to cover this with carbol fuchsin, and you want your slide to look like this when you make it. Here's your slide, and you want this to make sort of a church dome bubble. You want that carbol fuchsin to be like a bubble here. And you're going to pass it through the flame and out. Through the flame and out. Now, Mizuno and the other teachers give you a little clothespin so you're burning your little finkies. No! Hold the slide. Grow up! If it burns your fingers, you've exploded the bacteria. You're made out of the same thing the bacteria is. So if it gets too hot for your fingers, you won't know if you got a clothespin. So, put it in, hold it out, put it in, hold it out, put it in, hold it out. How long? Until that bubble shrinks. Until it begins retracting. Not until it's dry. Until it just begins retracting. Once you see the bubble shrink a little, shake it off, get your half a dropper full of acid alcohol, spray above the circle, and rinse off with water, shake it, and counterstain with methylene blue. So it's a lot like the gram stain without the iodine mordant, and you're doing some heating. Now, key word there is heating. Whenever you see the word heat, this is a key. This is a code word. You know what code words are, right? Code words is, let's go to this place over here. It's for our kind. People like us. You don't want to be racist, you know? But these are code words. Code words are secret communication that means something. And whenever you see the word heat, the secret communication we're trying to get across is, it's hard to damn stain this. It's hard. And if it's hard, you've got to involve heat. Now, in our class, in microbiology, name 3 things that are hard to stain that you may or may not have come across or have read about, or even used logic on one of them. We already knew one thing that's hard to stain. What is it? Lipids. Lipids are hard to stain. All right? Anybody read ahead and find something else? Endospores. And the last one, you'll never guess, glass. Glass is hard to stain. Guess what? With carbol fuchsin, if you overheat it, every one of these will take the carbol fuchsin. Your glass will be hot pink and you can never get it out. Endospores will take the hot pink, but they're not Mycobacterium. And Mycobacterium will take the hot pink. So that's why you can't overheat it. You've got to just withdraw just a little bit. So remember, anything that's hard to stain under heat will take the fuchsia color, the hot pink carbol fuchsin. And the things that we are going to be working with, the ones we want to keep it, the lipids. But endospores may also, and that's the genus Bacillus. And that's the problem genus for this stain. And then You heat a glass hot enough and long enough, and it's going to be hot pink. So, that takes us to problem staining. And let's talk about problem staining. Remember, the carbofuscin gets trapped in this lipid layer here. And that's why that stains hot pink. But carbofuscin is again dissolved in both water and an alcohol, so some will reject it. So some of them will just stain the last color you put on, which is baby blue. So how do you read this stain? And the answer is one hot pink rod makes it positive. It has to be a hot pink rod. It can't be hot pink any other shape. It has to be a hot pink rod. One. So, what are they going to look like if you stain bacillus? Some bacillus will give you this appearance. Remember, the vegetative cell is going to take the baby blue. And when I ask you, what does the cell stain? If the cell is blue, you're going to say acid-fast negative. Even if you get this. You may see hot pink endospores, because they're hard to stain, they'll take the hot pink. You may see blue cells with empty holes in them. But the question I'll ask you on the acid fast is, what does the cell stain? And remember, endospores are not cells. They are just DNA with a spore coat around them. They don't have a mitochondria, they don't have a nucleus, they don't have a membrane. They are just DNA surrounded by a spore coat. They are not cells. So this is endospores, and they are survival structures. Not cells. This is called the vegetative cell. So whenever I ask you on an acid-fast stain, what does the vegetative cell stain? If you're looking at bacillus, it's going to be baby blue. The hot pink is endospores. They're not cells. Somebody tell me why they're not cells. Why are endospores not cells? They don't have any cell parts. Do they have an endoplasmic reticulum? No. Do they have a ribosome? No. Do they have a nucleus? No. Do they have a membrane? No. What do they have? DNA and diplocholinic acid around the outside and calcium. That's it. So just having DNA doesn't make you a cell. Okay, so I want to show you a few things, a few pictures, and then I'll demonstrate this, and then we will have a little quiz and do it. And I just want to show you mostly the problem stains. Is it coming up? Yes, good. Can I have all the lights off over there? And if you could prop that window open, that door open just a little bit. All right, so we're going to look at some example stains here on Name the Stain game. This is actually E. coli or E. aerogenes or